Hello, thanks for tuning in to my talk today. My name is Ryan Freeman. I work at Compass Technology Group in Alpharetta, Georgia. It's a suburb near Atlanta, Georgia. This project is a collaboration between our company, Aerobotics in Huntsville, Alabama, and Mantech from the Air Force. We're going to be talking about a project where we take microwave spot probes, essentially handheld antennas, and scan aircraft radomes, and then take those measurements to determine the likelihood of defect. So, brief outline. First, I'll talk about the hardware, some background on radomes in general, and then two specific processes that we use to analyze the measurements of the radomes. First process is based on inversion algorithms. The second process is based on fitting the line shape of the spectra that we measure. So we have these different measurement analysis techniques, and I'll show how we can use them to identify defects, specifically delaminations and water content, waterlogged honeycomb core. So these are going to be shown for the frequency range from 2 to 18 gigahertz, but we'll also show proof of principle for the case of 20 to 40 gigahertz. So, quick introduction on the hardware. Again, is most of this is based around these microwave spot probes on the left. The SP218 is a probe that we have designed and manufactured here at CTG. Works from 2 to 18 gigahertz. That's most of the results I'll show today, but we've also more recently designed and fabricated this 20 to 40 gigahertz probe. So these probes are small. VNAs these days are small, so you put them together, and we have application based on the probe in both a handheld geometry, shown on the left here, and we also mount them to robotic systems. So the thing that makes it a spot probe and not just an antenna is that it is designed to have a 2-inch spot size when the probe is approximately 3 inches away from the surface you're measuring. So it measures this nice localized area right in front of the probe. Good for these handheld measurements. So the probe emits microwave energy, and then it is picked up again by the probe and goes into the VNA, and we measure reflected power as a function of frequency. That's a reflection spectra. So on the plot here, that's the y-axis is power, it's on a log scale, and x-axis is frequency. So this spectra is going to be our indication of whether our radome is healthy or defective. And I'll show this is a process designed around radomes, but it can be easily adapted to other types of dielectric components. So quick background on radomes. A radome is a mechanical shell that protects a radar antenna from a harsh environment, such as fast wind or rain, for instance. So mechanically it protects it, but then electromagnetically it is transparent in some given frequency range around the operating frequency. So it acts as a window to the radar. So there's several different topologies or like styles of radomes. There's the solid composite, which is just a solid material. There's A sandwiches, where there's this spacer material, this low dielectric spacer material that separates the two composites. If we invert that geometry, then we have a B sandwich radome. And if we stick a few more layers into the mix, then we have a C sandwich radome. These materials are, by design, low loss, and common materials for spacers include honeycomb or foam, and common material for the composite are fiberglass or plastic. So we talked about mechanical design of radomes and a bit about the electromagnetic design of the radome. The radome is, like I said, is transparent at this particular frequency. That transparency is because of a resonance. So we'll look at our diagram in the top left. If we have radar energy coming from the left, going through the radome and going out towards the right, we have the energy that's transmitted through the radome, but we also have some energy that's reflected from the front surface and the back surface. And when those two reflections are completely out of phase with each other, then you have interference, destructive interference, and the amount of energy that's reflected is minimized, and that maximizes the amount of transmitted energy at that frequency. So it's that working principle by which the radome is transparent at the radar frequency. So this resonance frequency is a function of the material properties of the radome. On the right, we have this expression for the resonance frequency. There's D, the thickness of the radome, and epsilon, the permittivity of the radome material. In this case, we're just talking about a single slab radome. It'd be a more complex expression for the different geometries, but same working principle. And then N is just the order of the resonance. Here we're just going to be talking about the first order interference null, but there's, as you go to higher and higher frequencies, this resonance, this interference condition is met again and again and again periodically, captured by this N. So the radome is, the properties of the radome strongly affect its spectra, or conversely, we could say the spectra contains useful information about the radome's physical properties. We're going to use this spectra that we measure from our probe to provide information about the health or potential defects in the radome. The way that we do this is by a series of experiments and models, kind of going hand in hand. We fabricate these mock-up basic A-sandwich radomes where we have fiberglass shells separated by this honeycomb core. We have a basic electromagnetic model that ends up being surprisingly accurate, and between the two of them working together, we find trends that allow us to identify particular defects, in this case water and delaminations. So the first technique that we use to analyze the radome spectra is the inversion algorithm. So this is a combination effort between measurements and modeling. So we take a measurement of the reflection spectra, and then we need a model of the reflection spectra. So this model is, in this case, if we look now on the right, it's called a transmission line model. It's a one-dimensional model in this case. So it pretty much just assumes that the sample is uniform in plane. So it's a good approximation for these planar samples that I've made. And in the model, each layer is defined by its permittivity and its thickness. So the physics that the model accounts for is reflections at interfaces between materials with different impedance, and the phase accumulation that develops as the microwaves pass through the material. So now we have this model, which is a function of the physical parameters of the medium, of the sample under study. So we take our measurement and we take our model. Now we use fit parameters. We take one of those physical parameters, the thickness of the radome. We adjust it until the model gives the same spectra as what we measured. And then in that case, we fix that parameter. We say that we have inverted the, in this case, physical thickness of the radome from a given measurement. So that inversion process, I'll show how we can find trends in that to identify defects. Similarly, here's another technique that we can use to analyze the spectra. So in the last case, we talked about this physics-based model. In this case, there's no physics. There's no assumptions about what we're looking at or what it's made out of, or any kind of like physics under the hood. It's just a basic line shape fit of the spectra that we're recording with our hardware. So these expressions are empirical. They're not based on any derivation. They are expressions that I found that accurately match the spectra that I get when I measure these radomes. So on the left we have our amplitude spectra. That's the power as a function of frequency, and on the right we have the phase spectra. So that's the phase lag between the microwaves as they're emitted and when they're picked up. So for the amplitude spectra on the left, we have this linear background, and then on top of that is the radome null. It's a Lorentzian. So this equation has 5 fit parameters, And if you initialize your parameters nicely, then the fits come out very cleanly and easy. And I'll show on the next slide how we can start to see defects associated with particular behaviors of these fit parameters. Similarly, on the right, we have our phase spectra. We have this linear background, and now instead of a null, we have this abrupt phase shift that happens at resonance, and we can account for that by this hyperbolic tangent function. So those are our basic techniques, and then we implement them in this experiment, a series of experiments and models. Fabricated 2 pristine radomes, and then 5 radomes where I've introduced delaminations. You can see in this picture, because of the translucent fiberglass, you can see underneath that there's this fiberglass window. So the window is made out of a thin fiberglass sheet. We know how thick it is. And in the middle, there's nothing. So it's like an air gap of a known thickness introduced between the fiberglass and the honeycomb. This is our delamination. I've made a series of these spanning from 0 mils delamination, pristine, in 10 mil increments up to 50 mils of delamination. And for those not familiar, mil means 1/1000th of an inch. It's kind of a weird unit. It's not a millimeter. So looking at the results on the right, top left, we have our experimental spectra. And so black is the pristine radome, and as we get more and more red, the thickness of the delamination is increasing. And then on the top right is our modeled result. And you can see that these two match really, really well. Which was kind of a surprise to me. It's cool when things work out the way you expect. So on the bottom, we take our these spectra and we perform inversions on them. This 3-layer inversion where we invert the thickness of the honeycomb and the thickness of the fiberglass layers. And you can see that as the delamination thickness increases, the inverted fiberglass thickness is not affected, but there's a strong effect, a linear relationship between the delamination thickness and the inverted honeycomb thickness. So as the delamination increases, the inversion model is picking up a thicker honeycomb layer. So this is a way that you could identify a delamination. If you know what your radome is made out of or how thick it's supposed to be, and you perform inversions and you get a honeycomb thickness that is too thick, then that is an indication there is a delamination. So that was based on the inversions. We also have the line shape fitting. The line shape fitting also ended up being a good way to identify delaminations. In this case, the most obvious result is that the central frequency decreases, the resonance frequency decreases as the delamination increases. And the other result, which is really just interesting to me, is that the line shape fitting allows you to predict which interface the delamination is on. So the red curve corresponds to the delamination being at the front of the radome, and the black curve corresponds to the delamination being at the back. And the line width of the curve is actually different in those two different cases. So the inversion method doesn't show you where the delamination is. It tells you that it's just there somewhere. But the line shape fitting can tell you where the delamination is, which just kind of shows how useful this technique is. So the next step is identifying water that's present in the radome. So for this experiment, we take these radomes, we drill 8 mil holes, that's 8/1000ths of an inch. We drill holes into the shell, and we inject water from a hypodermic needle into the honeycomb core. So if we're talking about inversion models, inversions require measurements and models. To account for this water in our model, we're going to use this Debye permittivity. So permittivity is a function of frequency that characterizes pure water. So we did a series of similar measurements and models, and we have these different trends that were found to be associated with the presence of water. So the first is just the simple case that 3-layer thickness inversion. Again, that's 3 parameters. In this case, when the outer fiberglass thickness and the core, the fiberglass thickness increases, the inverted thickness is thicker than it normally is, and the core thickness that is inverted is thinner than it normally is, then that's an indication that there's water present. Our next model is a different inversion model, but it's similar. In this case, I fix the 2 fiberglass layers to be equal to each other. So now we just have 2 fit parameters instead of 3. This is not explicitly true, but it does decrease the number of fit parameters, decreases cross correlations, gives a nice robust result, and we have similar trends. The third case is trying to account for the water in the inversion model itself. I tried several different ways to do that. The best results that I got came when I modeled the water as a thin layer at the back interface of the radome shell and honeycomb. So water layer inside the radome. You invert the water layer thickness, like an effective thickness, and the core thickness. So a 2-parameter inversion, and water is indicated by an inverted water thickness more than 0.5 mil. If that's your result, then it's strongly associated with water content. And the last result is, the last trend comes for that line shape fit again. This is a really big, obvious result. The line width, the width of that radome null dramatically increases as water is introduced into the radome. So we found these trends, and we can put them together into a process. So on the left, I'll talk about the process. On the right, I'll show 2 experiments where we show the results of the final defect detection algorithm. So the process is, first you measure the reflection spectra with our microwave probes, and then you compare the measured spectra to your expected spectra. So for this process, you have to know what your radome is supposed to look like. So if you compare those two, and there's a big difference between the two, some threshold that you set, then you'll say that the radome is of questionable quality, and you need to proceed with defect detection. At this point, the inversions and line shape fits that I was discussing are performed, and if those data analysis techniques, if the results match up with any of the identified trends, then a flag for that trend, for that defect, will be recorded. So at the end, the defect with the highest percentage of flags is reported as the most likely defect. So now the results on the far right, top far right, we have our waterlogged radome. We have water in the central area of the radome, 3-inch by 3-inch square. We're taking our probe and scanning it as we get closer and closer to that waterlogged area. And you can see that as we approach and ultimately arrive on top of the waterlogged area, the water flags are being registered, and there's no indication that there are delaminations present. So the other case is the delaminated radomes. Here's the result of one of the delaminated radomes. I think it's a 50 mil delaminated radome. And in this case, there's no water that's present or detected, and every one of these 16 random measurements along the surface correctly indicates that there is a delamination at the front surface of the radome. So the last step is showing how we can upscale this to higher frequency ranges. This will be useful in the near future, with 5G technology coming out. Everybody's going to higher frequency. So we do have this SP2040 probe, works at this frequency range, and designed and fabricated recently. We've attached it to this Anritsu high frequency VNA, and we take our probe and we scan it along the surface of one of my radomes where I've fixed these strips of painter's tape, and the thickness inversions correctly identify the presence of the tape. So it's just kind of a basic proof of principle of what you can do with the inversions and this high frequency probe. And potentially more interesting on the right is it's the same model that I showed before, where black The black curve corresponds to the pristine radome, and as it gets more red, delamination thickness is increased. So it's the same model as before, but now I'm showing it for higher frequencies. So down at 9 gigahertz is where we saw that radome resonance before. But there's also these higher order interference nulls at higher frequencies. And what you see is that the delamination has a much larger effect on those higher frequency nulls compared to the primary radome null. And that suggests that there's some defects, in this case delaminations, that will be easier to identify at these higher frequency ranges. So that is very interesting to us moving forward. And with that, I'll flash this conclusion slide. We have these 2 to 18 gigahertz microwave spot probes, measure radomes, have a defect detection algorithm based on these 2 measurement analysis techniques, and we can predict the most likely defect that's present, and we have plans to move it to higher frequencies. With that, I will entertain any questions.